Hello, this is the first video in our series on graphing. Let's start by exploring the concept of a function. Since graphs are closely related to functions, we'll begin by defining what a function is. To define a function, we need its domain and the rule that maps element to the domain to the range. Generally, the domain and mapping rule of a function are represented using specific symbols. Let's consider what elements are necessary to convert this into an interface. First, since the domain is a type of a set, we can use the previously defined concept of a region. The mapping rule, which sends an element from the domain to an element in the range, can be represented using the interface called map. So what exactly is a graph? A graph can be considered as a set of ordered pair consisting of points from the domain and the points from its range. The important thing here is how we visualize the graph. Because we live in a three-dimensional world, the simplest way to visualize a graph is to display it on a two-dimensional plane. A two-dimensional plane can effectively represent one-dimensional element, such as line segment. Although it's possible to project three-dimensional shape onto two-dimensional plane, this relies on our imagination, and what we clearly represent in two dimensions are actually one-dimensional shapes. Therefore, when visualizing a graph, it's necessary to convert the graph into a set of line segments. Now, let's think about how to actually draw a graph. For instance, in the case of single variable function, where the domain is one-dimensional and function maps each value in the domain to a real number, we can divide the domain into smaller intervals, plot the function values at each of these points on two-dimensional plane, and then connect these points with line segment to represent the graph. If the domain is two-dimensional region, we divide the given region, plot the function value at each divided grid points as points in three-dimensional space, and then connect those points with adjacent points to represent the graph. In other words, to create a graph, we need to divide the domain, calculate the function values at divided point, plot these points in a higher dimensional space, and then connect the adjacent points with line segments. Expanding this concept further, while a function requires a mapping rule from the domain to the range, to draw a graph, we need a function that lifts the point in the domain to a point in a higher dimensional space. For example, to draw the graph of a single variable function, you need to lift the point from a one-dimensional interval in the domain to a point in a two-dimensional plane. To draw the graph of two-variable function, you need to lift the point from a two-dimensional region in the domain to a point in a three-dimensional region. Therefore, we can define an interface with graphing called grapher. This interface should contain information about the domain, so it must include the region interface. And it needs a lift method that lifts the point in the domain to a higher dimensional space. If the lifted point is two-dimensional, it can be directly visualized on a two-dimensional plane. However, if it's a three-dimensional point, it needs to be projected back onto the two-dimensional plane. So, project method is also necessary. Meanwhile, the continuity of a function can affect the shape of its graph. For instance, the function 1 over x is discontinuous at x equals to 0. However, depending on how you draw the graph, it can either appear disconnected or look like it's connected by a steep line segment. To express this concept of continuity, you can use an interface called continuous. This interface requires a mapping from point to vector and, additionally, needs an EPS method. This method predicts how much function value will change at a certain point. It is based on concept of continuity from epsilon delta definition. In other words, when a given point in a domain and the radius around that point, it returns the maximum change in the function value. If the actual change in the function value is greater than this, the function is considered discontinuous. Now, let's implement a function that draws a graph based on these concepts. The graph function takes a variable of the grapher type and number of divisions for drawing the graph as input. This function draws a line segment to visualize the graph, and a line segment is determined by 2 points, the start and end points. The graph function returns these line segments as a channel. The first step in drawing graph is to determine the dimension of the domain. The dimension of the domain is the same as that of the reference point within it, and this is stored in the variable dim. Next, the given domain is divided, and each divided point is lifted to a point in higher dimensional space. The important thing here is to identify what the neighboring points are for each point on the graph. To do this, we use a function called neighbors. This function returns the neighboring point of a given point. The line segment connecting the 2 points P and Q obtained in this way is called a line. If the GPR variable implements the continuous interface, it can determine whether the line segment actually belongs to the graph. The distance between 2 points in the domain is compared to the function value distance obtained from the APS method. If the change in the function value is within this expected value, then the line segment is returned. If the GPR variable does not implement continuous, all line segments are returned. These returned line segments cannot be visualized as they are. Let's think about how to represent them in an image file. Here, we use structure variable called graph option. This variable contains fields such as number of divisions, domain range, and image size and the file name. To save the graph as an image file, we use save method for this struct value. The save method outputs the graph information to a file. To draw the line segment returned by the graph, we use drawLine method. This method converts point to pixel coordinate and then draws a corresponding line segment. In this process, functions like max, abs, and linspace are used. Let's look at the pixel function. The pixel function converts coordinate to pixels. Linspace is a function that evenly divides the interval between 2 points. Max and abs are functions that return the maximum and absolute value respectively. This concludes our explanation of the basic method for drawing graphs. In the next video, we'll implement the types needed to actually draw these graphs and look at some examples. Thank you.